everyone. Thanks for all getting here. I know we're a minute over, but I'll just give it one more minute for a couple more people to join, and then we will get started. All right, looks like we're 2 minutes after. I'll just get started with a little intro here. Thank you everyone for joining. Really appreciate you coming here on a Tuesday. Just a couple of notes. This presentation is being recorded, and the recording and the slides will be distributed by the end of the week. All other presentations are on our website in the archive folder, and our website just went under a little change. Our projects page is a little bit more user-friendly, so if you want to check out our projects, active, completed, all of that is on our website. With that, if you have any questions throughout the presentation, please feel free to drop your question in the Q&A in the chat or raise your hand. If you raise your hand towards the end of the presentation during Q&A, I can take you off of mute and you can ask your question live. Other than that, looks like we are ready to get started, and I will hand it over to our presenters.
Thanks, Kate. So thanks all for joining. My name is Madeline Talebi. I'm going to be presenting on the Gas Emerging Technologies program, specifically the project that we did in collaboration with GTI Energy for the adsorption gas heat pump lab tests. And then just to acknowledge some of the project collaborators, those from ICF, Stephen and Alfredo, and then GTI. This is a non-exhaustive list. There's probably more folks that I've missed here, but some of the main people, Jason, Alejandro, Lee, and then Rami will be co-presenting with me. And so just a brief agenda, so I'll touch on why we're interested in water heating in California, some of the objectives. We'll go over the test plan, some unit validation, and then the main bulk, which is the laboratory testing, and then looking at some techno-economic analysis and future recommendations for the project. So briefly, California on emissions control, why we're interested in water heating specifically. So it is the largest end use of natural gas in California. And then if we look at natural gas consumption according to end use, according to sector, we see industrial, commercial, and residential have the highest impact. And so looking at California legislation, so between Title 24, our building energy efficiency standards, and then Tech Clean California, just a couple California legislations that would support us looking into water heating specifically for the residential sector. So not the highest in terms of consumption, but still a sizable impact that can be had. And so the technology in this case is going to be a gas-fired adsorption gas heat pump. So you'll see it abbreviated as AHPWH throughout the presentation. So this is going to be essentially focus shifting to development of highly efficient thermal heat pumps for residential water heating. So we'll call this unit manufacturer A for the purpose of the presentation. And then we have essentially the evolution of the unit displayed down here. So the first, second, third alpha. Third alpha is not pictured. Testing was not done by GTI Energy, but those are somewhat of the succession of the iterations of the unit that have occurred. And then this last picture on the right-hand side is going to be the expected final product. And so the objectives for this testing, it's to improve the low uptake at the sector level, so that being the residential sector, continue to develop the technology towards a technology readiness level 9, just because this is in its a beta phase. And then to look at the technology performance and validation in a controlled environment, so that being the lab study, and then looking at a techno-economic analysis as it relates to the California market, and then recommendations for the prototype improvements moving forward. So I'll touch briefly on a system description. So essentially, this is the unit. There's two different figures listed here. The left-hand side is a bit more intricate. The right-hand side is, you can essentially look at it as a zoomed out image of the buffer tank itself. So really this unit can operate in two different phases, or two different modes, we can call them. So one being the direct firing mode, or two being its heat pump mode, or it's essentially a batch mode, where it would cycle between a desorption and adsorption process. So in this desorption phase, you'd see ammonia on this salt reactor that I have pictured here on the left-hand side. It'd be desorbed from the salt matrix, we're calling that the reactor, at high temperatures, and then subsequently moves down to the evaporator that we see on the bottom here. And then so under low fire, essentially ammonia would be desorbed, which nearly transfers all the heat to the indirect storage tank, or that buffer tank, as ammonia condenses. And then alternatively, in the absorption phase, we have low-grade heat and it absorbed from the air into the evaporator. The ammonia then evaporates and would move back to the salt matrix. And then when ammonia is absorbed into the salt of the salt reactor, the heat of reaction is supplied to the indirect tank again, or this buffer tank. And you can see on this right-hand image, there's 6 different thermocouples. That's mostly intact to measure the temperature stratification that Rami will go over in one of the later slides. But again, I have the main process mechanism listed at the top here, and then some parameter specs listed for this type of technology. And so with that, I will go ahead and pass it over to Rami.
Thank you, Madeline. This is Rami from GTI Energy. So once you receive the unit, we do like a commissioning test. One thing we need to figure out first is the system's function once we receive it. So we install the unit at GTI Energy, one of residential water heating test bed, to make sure the firing is good and everything was working as it should be. So the first thing, we heated up the tank using like a 7 kilowatt firing rate, and make sure this like a temperature stratification is well established. As you can see in these 2 diagrams, firing rate is almost constant, so they have a stability in the combustion system, and also the tankless can maintain like stratification. So once we heated up the tank, we let it to cool down. Next. So we need to cool it down to assess the installations that we added to the tank. So let it down, let the system cool down for a longer period of time, almost like 1 day, and we track the average tank temperature. So we found the tank lose about like 0.5 degrees C every single hour. So this is translate to a heat transfer coefficient, or like thermal losses, about like 7.8 BTU per hour per Fahrenheit. This is a good number. So the heating system is working good, and also the installation in a good phase. So we can start the main testing. Next. So then we did like a DOE standard evaluation for this, including the first hour rating and UF. So we did the first hour rating, how many gallons can this tank deliver over the first hour. So we use like a one firing rate. So we assume to be like 2.8 kilowatt, which is like about like 9.5 MPH. We found that can deliver like 22 gallon. Before we getting this unit, the manufacturer did test at the maximum firing rate, which is like 7.3 kilowatt, and the manufacturer calculated like 51 gallon per hour. So this is set this technology at a medium draw better. So based on this, we moved to the UF. So we applied the standard profile from DOE and using a medium draw profile, and we did the first the UF test. Next. So this is just like a zoom in about the first canister. We completed the 24 hours. This figure shows the first canister. We see this is like, as Madeline said, this is like a desorption phase following by adsorption phase. When you see like red lines, means the firing rate is the burner is running, and this is like a modulating burner. And then around like after 60 minutes, desorption completed, and then we go to like the second phase, which is adsorption. The system is able to lift some energy from the ambient. So the total period, or the total duration of one cycle, is about like 3 hours. Next. So this is also like a zoom in about the average tank temperature. We would like to make sure we increase the tank temperature while there is draw going on. And then we need to make sure these temperatures keep going up when we have adsorption, meaning the system is able to lift energy from the ambient. As you can see on the left figure, the reactor cooling and adsorption begin at approximately the same time. So desorption and then pre-cooling is the tank is just like transition period between the desorption and adsorption. So this is after you complete the desorption, we see some increasing in the tank temperature. We mean that the system is able to lift some energy from the ambient. But after a short period of time, we see this curve going down with the same behavior like the standby losses, 0.5 degrees C per hour. So there is no more energy added to the tank by the heat pump effect. So this is some analysis before calculating the UF. Next. So another observation also about from the ammonia side. So we see during the desorption, this like a green line doesn't mean anything during the desorption, but during the adsorption, we saw this like green line, which is the ammonia temperature, goes less than the ambient temperature, which means that the evaporator is lifting energy from the ambient and put it into the tank and makes this increase in the temperatures that I showed in the previous slide. So just a summary of this UF test is we started with the initial tank temperature about like 130 something, and we ended up like 127 after 24 hours of testing. And the system is able to deliver hot water temperature all the time at average 121, which is really good, and keep the ambient or the inlet temperature all the time at like 58, 59 based on the standard. So overall, the tank deliver about like 55 gallon as a schedule, and also the standby losses is 7.14 BTU per hour per Fahrenheit. We calculated the recovery efficiency is 90 or 69, about 69%, and UAF came close to this value, which is like 68. So this 68 means that there's like need to be improved, and we need to work on the system to make it to the next level. But the main point here, the system is able to lift energy from the ambient, and the heat pump it's working. Next. So just like another test about emission to make sure this is like comply with the standards, we measure the flue gas temperature during the running of the burner during the desorption phase. We found the flue gas temperature is settling less than all the time like 30 degrees C or 95 Fahrenheit, which means that the system is condensing system because the dew point of this flue gas is less than like 57. We did like NOx and CO and CO2, all this number came to be comply with the standard ASHRAE standard and also other standards. So this profile suggested like high combustion efficiency. So from energy, we need to do much improvement in terms of mission and burner. It met the standard, which is good. Next. So now we have some effort to or some thought to improve this efficiency to push it more than one. And if we can push it more than one, how's it going to affect the energy saving compared to the standard gas-fired water heater? So we did some like techno-economic analysis, theoretical analysis using like the limit of this UF can exceed like 1.1, 1.2, and see what's the energy cost, utility bill, greenhouse gases. For this simulation or modeling, we use a BOPT, which is tool technically from DOE, and we simulated the residential load profile, and we assume like a single family home with like 4 occupants, and we compare this data with another technology. Next. So we assumed if this system, after further development, can achieve like high UF value, what gonna be the reduction in the energy saving or energy cost? So this figure shows that two different locations, Los Angeles and San Francisco, and show how much natural gas you're gonna reduce and CO2 emissions and your bill. You see about like 30% if we can improve this UF from 0.68, which is experimentally measured, push it to like 1.2 after further development in future, we can achieve about like 30% reduction in cost and also in the emission in two different places in California. So this result shows this technology is promising, but still we need to do further improvement in terms of design and also in terms of performance. This I think what Madeleine will touch on.
Thanks, Rami. So just to give some high-level key takeaways and recommendations. So overall, this study does align with federal initiatives and California decarbonization strategies, as I had mentioned at the beginning. So for the FHR test under direct fire, of course, it did result in a total draw of 22 gallons, roughly at about 9.5 kBT per hour firing rate. And then the unit achieved a UEF of 0.68 with a recovery efficiency of 69%, showing promising results, maybe not, showing room for improvement in terms of this. Again, this is a prototype model, so, but this is definitely a good start with that, this beta model, of course. And then looking at future studies, so with some of the results that Rami had presented on, so some of that essentially revealed that there could be improvements related to burner quality, material insulation, of course, and overall structural design. There's studies related to temperature stratification within the buffer tank. That would, of course, optimize absorption process and minimize energy losses. And then looking at the techno-economic analysis, which reflects that of the actual experimental results to quantify savings where the unit achieves a UEF greater than 1. So overall, some recommendations, improvements on the beta model itself that could essentially simulate better results, or I guess more favorable results in this case. And then just, this is part of the Gas Emerging Technologies program. If you have any questions or would like to get in touch, please don't hesitate to do so. I'll open it up to any questions that there are. We can put you off mute, or we can answer anything that comes through the chat. Not seeing anything. So I see one in the chat. Was only one manufactured study for this? Yes, this is only looking at a unit for one manufacturer. And seeing another one, is this technology approved by the CEC? I don't believe so, especially because it's still in its prototype phase. So another question, what improvements to the design do you expect to improve the UEF? So again, that could be, I think, a number of things. I think speaking with the manufacturer, speaking with GTI Energy, and Rami, feel free to add additional information, but it's really, I think the burner needs a little bit of a restructure either on quality and material and or on design itself. And Rami, if you have anything additional to add.
Yeah, I can add more here besides what you said, Madeline, is the thermal compressor of the system, which is the reactor. So we need to do some improvement in terms of how we're gonna generate the ammonia and absorb the ammonia, and also the temperature stratification inside the tank need to be improved because during the adsorption we need to get like cold water, which is not cold, but like less than 40 degrees C to be able to facilitate the adsorption. And as the curve is showing, like temperature increase and after a short period of time decrease because the adsorption period was very short. So we need to extend this duration or operation by improving the reactor design. Yeah, that's exactly what. Thank you, madam.
Mhm.
So technically, we need to be able to like lift more energy from the ambient to exceed the limit.
Would it be, so another question, would it be legal to install it in California? What would be the timeline for getting it CEC certified? I don't, I'm not too sure. I don't know if Stephen, you have additional insight on this, but I don't believe we could install it. I, I guess outside of maybe a field study in this case.
Yeah, I'm not really sure of the code process to get things approved, but obviously they would need to get all their, UL and ETL and everything else dialed in as well.
Also, we need to keep in mind this is emerging technology. So this is after like fully develop this technology, we need to go through like this certification and also some compliance with the DOE standard as well and AHRI. So there's many things in terms of regulation need to be done, but after fully develop the system.
The manufacturer has requested to be anonymous, so I won't be able to share, unfortunately.
Um, Technically about the commercial water heating application, no, this is a residential application made in medium draw profile. So we see this is a gap here in this category. So this is why this manufacturer focus on residential medium draw profile. Will you be following up with some of the future study recommendation as a next step? Yes, this is something will be released this year about more improvement related to this technology.
Any further questions?
Yes, the final report for this study is available on the website. I can see if I can grab the link real quick and drop it in the chat.
Were you able to find it?
Yeah,
Oh,
I,
there you
yep.
go. Well, I appreciate the presentation. Very interesting technology. And thank you all for attending if there's no further questions.
Thanks all.
Have a good day.